Okay, great. Very pleased to have everyone here for Peter Hase's defense. Peter has worked a lot on interpretability and model editing as part of controllability in language models. He's also a Google and before that a Royster Fellow at UNC. He's also done a lot of good community work for our conferences, including I think he was one of the best area chairs at ACL. He's also done a lot of collaborative work across different communities interested in these topics. So today he'll be talking about interpretable and controllable language models. Let me also briefly introduce the committee. So we have Professor Srivastav and Professor Sridhar from our department at UNC, and then we have Professors Anna and Samir from Utah and UC Irvine joining us as external committee members. So thanks everyone for attending. Peter, you can take the floor.
Yeah, great. Yeah, thanks so much everyone for being here and excited to give you kind of the final defense here of the work we've been doing and the thesis work. So today I'll be talking with you about interpretable and controllable language models. Okay, so to begin, what is the point of this thesis? The scope of our work is that, okay, so language models are getting better at many tasks. That's kind of the world we live in today, and this kind of artificial intelligence is getting better at many tasks. But we do not know their internal reasoning processes. So typically, when language models do interesting things and solve difficult, interesting tasks for us, often we don't necessarily know how they do this and what kind of reasoning they use. Additionally, we train models, and that means we teach them to do a task as a whole, but often individual behaviors are hard to manipulate. So we have an AI system that can answer a wide variety of questions or process different documents for us or do valuable things with text. But if an individual, if there's an individual mistake or an individual answer to a question that we don't necessarily like, often it's hard to know exactly how we would tinker with that AI system in order to adjust that behavior for the better. We lack this kind of fine-grained control often. Okay, so these are two problems. Okay, so the main goals of our work have been to develop and evaluate tools for firstly explaining why language models produce the outputs they do. So that's better explaining how the systems work. And secondly, exercising fine-grained control of language model behaviors. So that's being able to do this kind of like low-level tinkering with the AI systems and being able to better adjust individual answers to questions or individual answers that they might give us. Okay, so that's the overall point of the thesis. Now let me try to situate us a little more even in kind of what's going on today. So I'm talking about language models. I'm talking about these increasingly capable and general AI systems. So the term language models is popular. Term large language models popular. Foundation models is a new and decently widely used term here. We're talking about systems that learn from a lot of data. And one of the key properties of these kinds of systems now is that after they've learned from a lot of data, they can be adapted to be able to accomplish a variety of downstream tasks. So we live in a world now where a bunch of data gets collected, often by companies, and they spend often a lot of money training a language model. And then this language model is basically surprisingly good at doing a bunch of things, like answering questions, sentiment analysis that's telling us whether text is positive or negative, or what kinds of emotions the text reflects, extracting information from documents, even things like seeing an image and writing a caption for what's going on in this image, what's going on in this image, and even things that push in the direction of like agency, like being an assistant or like following instructions and like carrying out a task, following instructions. So that's kind of the key property of these kinds of systems is that they're trained on a lot of data, they're increasingly capable for a wide variety of tasks. So there's a lot of work going on now in improving large language model safety. I won't really go into a lot of the background on safety here, but I think it's worth pointing out that this really has been a lot of the motivation for work in my thesis. And it just happens that we've been doing technical work. So I want to try to describe where in the overall pipeline our work falls. So there's a lot of work going on in model pre-training, which is like you're building the LM, you're building the foundation model. And I think there's valuable safety work going on there too. So people do research on better understanding, okay, based on properties of this learning system, based on properties of this data that the system's learning from, what kind of behaviors will we expect it to, to be able to execute at the end of the day? What kinds of, basically what kind of capabilities are we actually going to achieve with this system? So there's work on better understanding and predicting what kinds of capabilities arise after you set up some kind of training process. So that's actually not something we end up doing, but really we end up doing a lot more things focused on model deployment. So this is like you have a large language model. So someone built a large language model, and there are things you want to do mostly after the fact that you think will improve the overall safety of the system and make it work, really as intended and as humans intend. Yeah, I'll go into that more later, so I won't say as much on that now. I just think it's worth pointing out, again, that there's still a lot of socio-technical challenges here. And really, these are not like distinct aspects of the problem, but more like angles on just viewing the problem of how language models get developed and used in society. So there's a lot of ongoing and interesting work, I think, on how to shape the broader AI ecosystem, how to properly incentivize people to build safe models and useful models, how to incentivize people to deploy them in safe and in responsible ways. And I think a lot of this work is super valuable. It happens that I'm going to focus on, and the work we've done mostly thinks about model deployment. So it's like you have a language model and you want to do things to better understand it and to make sure it works as intended. So three topics I'll end up talking about, and this is what we'll go into next, is interpretability of these kinds of language models, fine-grained control, and lastly, some application work in deleting sensitive information from the models. Okay, so that's the roadmap for today. And on the first topic, I'll start trying to motivate what we want out of interpretability, what we mean by interpretability of systems, and then after that, talk about some research we've done in the area. And I'll do that for each of these three goals. Okay, so first, interpretability. What do we mean by interpretable? Okay, so we'll say a model is interpretable if we can form accurate beliefs about how it works. And by how it works, we mean, okay, there's some causal chain of events that lead the model to produce the outputs it does. An input comes into this machine learning system, the machine learning system does some processing and produces an output. We want to be able to better understand what are the events that occur inside that system that lead to the output. Why is this useful? Well, we're always going to be evaluating models with test data, and we're always going to be getting quantities like accuracy. So this is how, this is the first thing people often do when you train a model and okay, you want to know how well does it work. And so you have some test data and this produces like, okay, we're getting like 90% of the cases correct or 95% of the cases correct. And this is really useful for sure. I think there's something that can get a little deeper into like, does the model work as intended? Which is if we can verify the reasoning. So I'll go through basically an example of why I think this is useful. Borrowing from this argument from Alon Jacobi and others, I really like this figure that points out how like testing is this like slightly higher level emergent property and accuracy is this like slightly higher level emergent property of underlying reasoning. So typically we're doing testing, and I think what I want to argue is I think that what that gets us is that we know that the model works as intended, basically on the test cases, and maybe cases that are really similar to the test cases. But we know that machine learning models often fail in kind of surprising and unpredictable ways. So often we don't even have a strong guarantee that the system will work properly on cases that are similar to the ones we test for, but not exactly the ones we test for. So often testing can really only get us, I think, so far. Contrast this with explanation and being able to explain an underlying reasoning process. I think what this gets us is some measure of confidence that the model will work as intended in general. So it's like if you know the underlying reasoning process, you should be able to say, okay, these are the kinds of cases that the system will handle properly, and these are the kinds of cases that the system won't actually handle properly, because kind of truly how it works. And so it should give you this extra predictive power for when the model will succeed or fail. So I'll walk through an example to try to make this a little bit more concrete. This is an example I've adapted from a paper from Hibabindu, Lakraju, and others. So in this setting, you can imagine we have some model that's doing something like lung cancer risk prediction. So we have a question like, okay, so for women predicted high risk for lung cancer that are older than 65, why did the model decide to predict them as high risk? So it's like the model predicted high risk and we want to know why. So in a world where we do testing and we get accuracy scores, I think the answer is like, okay, well, the model says, I don't know, but the model's accuracy on this group is 90%. So maybe this accuracy is good enough to actually use this system in practice, and this system helps, medical practitioners do early screening and risk assessment of patients. And overall, that this system is still useful. But it seems like something's lacking if this is kind of the ultimate answer to the question. And I'll contrast this kind of answer with, I think, one that's more informed by interpretability, which is you can imagine a system that says, okay, good question. Here's what's important to that prediction. It looks like the model predicted these individuals as high risk, mostly because they're smokers, but also because they live in large cities. It seems like this is the right explanation for the model we have based on some metrics of explanation quality. Here's a little graph that says what's important. And okay, so that's the explanation. It's like these are the features and how they're important. And I think this can get us a lot more immediately. I mean, first it might just be like, okay, yeah, this seems like the right way to assess if people are high risk. I think one especially important thing here is that it lets us start to question how the if the model works in the way we think it should work. So it might be that we're surprised that, oh wow, I didn't realize a person living in a city was so important. Like, are we sure that's a good reason? Do we want the model to be relying on that? To what extent does the model really rely on this? And we can start to dig deeper, and in this setting, we can start to make quantitative claims, and this is like coming from actual empirical work in the area. You can make quantitative claims like, yes, this factor is important. Like if we look at this model counterfactually, sometimes, changing whether someone lives in a city or not changes the prediction of the output. So if you take the same person that hadn't lived in the city, the model wouldn't have classified them as high risk. And I think this kind of process and this kind of digging deeper can give us a much better understanding of models, not only so that we might trust if they'll actually generalize properly or if they're working intendedly, but also so we can start questioning them and ask, do they work in the way that we think is correct? If they don't work in the way that we think is correct, can we start fixing them and adjusting them at that point? And I think all of this kind of analysis is very complementary to testing, and it gives us information that is complementary to just accuracy information. Okay, so that's the pitch for why interpretability. Now I'll talk about some research we've done in the area. So it'll be based on this paper, which was published a few years ago at ACL 2020, and it's on evaluating explainable AI. So what we've done here is that we propose a study design for measuring something called simulatability of an ML system. An ML system is simulatable when a person can predict its outputs. Okay, so why is that useful? We do some kind of like backward inference from this result. Um, if you think if a system's simulatable, it's like a person must have a good mental model of the system. In order to like accurately predict what the system will do in new situations, you must have some rough, you know, um, internal like view or internal assessment of how the model actually makes its decisions, even if it's pretty rough. So then one thing we'll really look at in our study is if an explanation improves simulatability. So we think if an explanation improves simulatability, then the explanation must be revealing something about the causal chains inside the model, the causal chains behind the model behavior. And that's because, okay, if you think predicting the model behavior requires having a good mental model, and the explanation improves that mental model, it's like, okay, we're getting some deeper understanding into what actually drives the model behavior. We're going to summarize this whole argument by saying the explanation is faithful. So that's the term in the literature that people really look for and say, we want the explanations to be faithful. So the point of our user study is that we measure the effect of explanations on simulatability with the goal of being able to say what kinds of explanations are faithful or not. Okay, I'll describe some tests we use for this. So this is kind of a human study test we use. Uh, the basic setup is that we ask people to predict model outputs before and after individual data points are explained to them by some explanation tool. And our estimate of the explanation effect is how well people are able to predict the model outputs after seeing explanations versus before seeing explanations. That's this equation. To spell that out in some steps, how we actually run one of these studies, our forward simulation test, is we say, okay, first we're going to kind of generally show the model, generally show a human how the model works. So we actually give just examples of inputs and outputs to a person, what was the correct answer, and what did the model predict for that kind of data point. The second thing we do is we set this pre-simulation accuracy baseline. So it's like, now the person's kind of seen the model in action. How accurate is the person's mental model of the machine learning system? How well can they predict what the machine learning system will do? In this case, on test data. So it's actually new test data that's separate from the learning data. After we measure the quality of their mental model, kind of pre any intervention, we do our intervention. So the intervention is to now show the people explanations. So in addition to just seeing input and output pairs, we're showing people, we're going through individual data points and using some explanation tool to explain why did the model make the decision that it did for that data point. That's the intervention. And then we run our prediction test one more time. So we once again measure what we think is the quality of the human's mental model by assessing how well can they predict machine learning systems outputs. So we take these post-simulation scores and subtract off the pre-simulation scores, and that's the estimate of explanation effect. That's the first kind of simulation test. And then we have another one that's overall pretty similar. The main difference is just about what kind of data we're using, what kind of data we're explaining versus what kind of data we're testing on. The second test tries to pair data points so that you explain one data point and then you ask the person to predict what will the model do on a similar data point. So the graphic gets very slightly more complicated, but really the main thing to emphasize here is that you have two similar cases. You explain one case and then ask the person to predict the model's output for the second case. So the idea is that if the two cases are similar, we think the explanation might shed more light on the second case. That's the counterfactual simulation test. Okay, so we'll ultimately basically hire undergrads, run them through some tests, make sure that they understand what's going on, and then run them through our human tests here. Let me talk about some of the setup. So what we're doing is we're going to be training neural networks on two tasks. There's a sentiment analysis task and an income prediction task. We used 4 local explanation methods. I'll show examples of that next. And we ultimately collect just over 200,000 responses from about 30 undergraduates via some in-person tests. I can describe more details about some of the p-values and confidence intervals that we'll see in a second, but it's done by Bootstrap. Okay. So here's an example of kind of what's actually going on. It's like this is the sentiment analysis task. So the idea is you have some sentence. This is like actually an excerpt from a movie review. It's despite modest aspirations, its occasional charms are not to be dismissed. We show this sentence to a person. The label's positive. The model prediction's negative. We wouldn't show them the model prediction if this is a test data point. And the idea is like we want them to predict what would the model actually say for this kind of data point. But and most of this in many of the settings, this is like a training example for the person. So here are the kinds of explanations that we're using. So Lime is like a feature attribution explanation. This means you're like picking out words and saying these words have a positive effect, these words have a negative effect. If overall we think that there's more negative evidence than positive evidence, we think that the model will say negative. That's kind of a Lime style explanation. In the middle, there's like a prototype explanation. That's kind of an explanation by prototypical example. And it's like, okay, well, here's another data point that the model predicted is negative. And we think that this other data point is pretty similar to the current data point. So, last time the model said negative, we think that the model will say negative this time too. On the right-hand side, the decision boundary example is like kind of a contrastive explanation. So it's like, well, why did the model predict negative for this example? Well, one way to get some insight into this is to say, what would have to have changed for the model to have predicted positive? So you change some features in the input, you swap some words around, and it's like, okay, well, if these words had been different, the model would have predicted positive. It seems like these words are quite important for the model having predicted negative. Now, various kinds of explanation tools for saying, here's an individual example. Why did the model give the output that it did? Okay, so I'll talk through some main results and the main conclusions for which of these explanation tools helps people form better mental models of the systems. The first main result is that Lime really did improve simulatability for tabular data, quite a large effect size, like almost 12 points, like a little over 11 points. And it's like, going from people could predict 70% of the time what the model would do, it's like 82% of the time people would predict what would the model output for this kind of data? And that's across both kinds of simulation tests. Yeah, I'll go ahead and take a question, Shashank.
So these explanations, these are for the test data points themselves, or do the users just see these for some training examples?
Just see them for the training examples. Yeah, the test data itself is not explained. Yeah. Yeah. So for instance, in the counterfactual setup, it's like the explanation comes in for this X point, and then XC, which is the counterfactual point, is the point that we actually want to get the user's prediction on.
Thank you.
Yeah. Yeah. Okay, so that's one pretty positive result. There's one other positive result, which is the example-based explanations, which is the prototype explanations improve simulatability on one of our tests. At least it's like at a 0.05 p equals less than 0.05 threshold. This was across data sets, but it wasn't across both kinds of tests. So to be honest, I'd be like a little suspicious of this one. I'd hope for the result to be like a little more robust and hold across both kinds of tests. Apart from this, none of our other estimates significantly differed from zero, and that includes Lime for text, the prototype example-based explanations for one of our kinds of human studies, anchor explanations. I didn't go into detail on that, but it's just a third kind of explanation method. And then there's counterfactual explanations too, where we're like saying, what would it have to have been different for the output to have changed? For all these methods, we weren't seeing statistically significant results. And I'll pause here for a second and say, okay, like why was this surprising? I mean, these methods I think generated a lot of optimism in the community, particularly up to 2020 when we ran this study, particularly between like 2015 and 2020. And when people started to run them through slightly more stringent human tests, I mean, I think what's interesting is that, there were clear wins. Like Lime really did improve simulatability for this kind of income prediction task, which is like a low dimensional tabular task. And I think we have actually a good understanding from talking with our users about why that happened and like what they learned about the model. But then there were just also a lot more settings where it seemed like the methods weren't necessarily working well at all. So this was overall pretty surprising given the level of optimism, I think, in the community at the time. We also wanted to know if people kind of understood what was going on. So we looked at subjective ratings. We asked users if, when the explanations were good, and really that means we asked users to rate the explanations on a 1 to 7 scale and answer to the question, does this explanation show me why the system thought what it did? And then we estimated the simulation score from these ratings. So this is really like saying, the user will rate the explanation on a scale of 1 to 7, and then we can empirically test, did the explanation actually help them predict the model's behavior? And at least we found the results weren't statistically significant. The confidence interval is like somewhat loosely concentrated around 0. I don't want to say it's like exactly 0, but at the given level of power in our human study, we weren't seeing that users could actually tell when the explanations were working or not. Yeah, so it's kind of concerning because it could be that like people like see the explanations and develop some trust in the system, even if the explanations aren't really teaching them about how the system works. And I think we've seen this basically borne out by follow-up kind of HCI studies too.
So I have another follow-up question. Peter, can you go back to the previous slide? So can you describe here like what the p-values for these, so you're thinking of these as negative results, but so it's not saying that these do not help. It's just that in the study you did not find significant evidence for that.
Yeah, thanks, Shashank. I mean, that's exactly correct. And it happens that the results might have been like +2 or +4. Sometimes they're a little negative. I think over like a method might get +3 in one setting, but then like 0 in a different setting. It happens that like it'd be nice if there were like 10,000 responses rather than 2,000, and we could have really tight confidence intervals. Yeah, this is somewhat generic problem with this kind of like p-value based hypothesis testing.
Right. So like if we had a test saying there was no difference in this case, like would you think that a hypothesis test would say that, or is it just because maybe there's not enough power or like the sample size is too small to actually get significance?
In this setting, it'd be hard to make really precise claims about is the effect size 0 versus 2 versus 4, for instance, given the number of responses we had. Yeah, I think something that increases my trust in this kind of result, and actually I'll flash a slide up later that shows some follow-up studies, is that mostly when other people have run these kinds of studies, the overall trend is like surprisingly similar, even with different kinds of language models, even for different kinds of tasks, and even for different kinds of explanation methods too.
Thank you.
Yeah. Yeah. Okay, so I'll wrap up with some conclusions here. Lime seemed to work actually pretty well with this kind of low dimensional tabular data. So I realize I haven't exactly defined tabular data for some of the audience, but that means like data that's like a table, like there you have individual entries in the table with people, things like people's age, marital status, like well-defined things like that. Besides that, local explanations did seem to, at least according to the last kind of answer, they seem to fail to reveal how models work over huge data spaces. But then this also includes these kind of counterfactual scenarios where we are pairing up the data and just tweaking the scenario a little bit, and it still seems like the explanations weren't helpful in these kinds of counterfactual scenarios. And lastly, at least according to the subjective evaluation too, it also seems like users can't confidently tell when the explanations are good or not in practice. Yeah, so yeah, more context here. I think a lot, basically this kind of framework has been continuously popular in the literature, and there have been a lot of follow-up studies with, really large language models and including other kinds of ways that we might more naturally interact with language models, like getting them to explain their answers to us, like just in text. I think a lot of us will have had this experience with ChatGPT where it like gives you an answer and then gives you like a whole paragraph or like 3 paragraphs explaining its answer. Basically, a lot of these follow-up studies have gotten really similar results. Like often the models will say something that seems like a good explanation, seems pretty plausible, seems to increase user trust in the system, and that it's kind of knowledgeable and reasonable. But then when you actually run these kinds of simulation tests or faithfulness evaluations, the explanations frequently are missing important factors that are actually important to how the models work. These are 4 studies that come up with basically pretty consistent results in this direction. I'll mention 2 studies that I think one of the big next directions for work here, I think, is fixing this issue. So there's kind of new line of work here on trying to train the models to give more faithful explanations. And one of the recipes there is focusing on consistency across different data points. So yeah, once you give one reasoning process for one data point, if you're solving a different problem, you should not act in a different way or according to a different process. You should use some kind of globally consistent process. And that would help make the systems more predictable in practice. Okay, so that's some of our work on interpretability. After this, we'll switch gears a little bit and I'll start going more into fine-grained control. All right. Basically, I'm just going to define this with an example. Speaking of ChatGPT, I think many of us have also, had this experience of asking a ChatGPT question and getting an output that like looks pretty reasonable. Like it seems like this is like a confident sounding explanation or an answer to our question. It just happens that if you went and Googled this, like almost all aspects of the answer would be incorrect, at least factually incorrect in this setting. This is an example where we just asked ChatGPT a question this is a March 2023 example. And it's like, okay, well, this one answer to this one question was wrong. How should we go about fixing this? Okay, so what OpenAI is doing is they're investing a lot of time and effort and money into improving the system and making it more knowledgeable and making it better at instruction following and better understand users' questions to it. Okay, so let's fast forward 1 year after lots of effort at doing this and ask the system the same question. Actually, it's going to do a little better, but it's just still going to get a few things wrong. This is nitpicking a little bit. Sometimes it's just a date. Sometimes it's like one word, but it's not exactly correct. And we spent a whole year trying to make the system more knowledgeable. So basically, the usual argument at this point is how should we respond to these kinds of errors? Well, pre-training and fine-tuning these large models over lots of data is expensive. We can definitely identify errors, but we want to avoid these kinds of really expensive retraining, costly in terms of time and resources. We want to avoid these kinds of retraining processes. It'd be nice if we could fix errors one at a time. We see the errors come up, we just want to be able to say, the answer to this question is, Y rather than X. And if the model could just learn from this feedback on this one question, that just seems quite practically useful. I'll add to this kind of, it's a typical argument that it's not even clear that, some people have cast model editing and this kind of fine-grained control area as like, well, it just kind of seems like fine-tuning, right? It's not clear that more traditional training methods like pre-training and fine-tuning are actually even going to solve this problem. The example I was just showing, we have this question. The answer is on Wikipedia. So if you look up this person on Wikipedia, there's just like a list of awards and like there are references for all of them. Um, the Wikipedia is like almost definitely, the data sets that people train these models on are proprietary, but Wikipedia is like definitely in the data. The answer's in the data. You spent like a lot of money fine-tuning the model on the like training and fine-tuning the model on the data. It's just not learning the answer. So it seems like we may need some additional toolkit for being able to make these kind of fine-grained edits to fix individual errors in the model. It's not necessarily the case that this previous paradigm of training on tons of data all at once will ultimately produce models that like have good factual knowledge. Okay, so that's the argument and a bit of context for what I mean by fine-grained control here. Now I'll talk about model editing. So a little bit of background on model editing. Here's some work from Nicola Takao and others where, particularly around 2019 and 2020, people are noticing that like, wow, these language models really store a bunch of information about the world. And you can ask them questions, and often you can probe the model or get the model to answer the question in a way that they kind of know a lot of trivia. But they don't know all the trivia. So the models will still get things wrong. And basically, following the argument I gave before, wouldn't it be nice if we could edit the model to be able to give more accurate answers to questions, like one question at a time? Something that this work does is it starts to lay out like, okay, so what are our goals when we're doing this kind of model editing? In this case, we want the models to generalize across paraphrases of the question. So you ask a question one way and you update the answer to that specific phrasing of the question. You don't want the model to give you the old answer if you just tweak the question slightly. So if you're basically just asking the same question two ways, you want the model to be able to give you the same answer, as long as it's the same question. Okay, so this is thinking about kind of evaluation cases we'll be interested in. So I'll talk about some research we've done in the area. Quick word on terminology before I actually show you the paper. We're talking about editing. I think this is basically, editing and updating and revising are all basically the terms I'll be using here, and I think pretty reasonable terms. What are we editing? Well, so a lot of papers have discussed editing facts and knowledge in the models. To me, I think it's a little awkward to describe this problem as like knowledge editing if like the information isn't true, or it's like hard to say when language models like truly know something. I actually think the word belief feels appropriately weaker and more appropriate, and that's based, more or less on this characterization from Daniel Dennett of a belief as an informational state that's decoupled from any motivational state. So yeah, it happens when I've spoken to philosophers about this. I think this is the minority view in philosophy. This is a super stripped down view of what a belief is. But I think it's also a simplifying view, at least for our purposes. We're talking about information models. I don't think we want to make strong claims about whether like the models like truly know facts about the world or not. But I do think we want to be able to speak about editing information and updating information in models. So often I'll refer to that kind of information as beliefs. Yeah, there's more to say for like, truly if what it means for models to like have like truth-oriented beliefs or even, something approaching knowledge. But yeah, and kind of lastly, the thing I'll add here is like, for what it's worth, the problem has also been historically called belief revision in computer science and philosophy. Okay, so that's a lot of preparation basically for saying this is why we when we're working on this problem, we ask the question, do language models have beliefs? And we presented some methods for detecting, updating, and visualizing model beliefs. Okay, so practically, what are we really doing here? So 2 main research questions in this line of work. Number 1, how should we evaluate model edits? And number 2, can we continually update a model with new beliefs? Number 2 is important here because, okay, models make, more than one mistake. They make mistakes over time. We want to be able to update the errors over time in the model. Okay, so first, how should we evaluate model edits? You can imagine a situation where you have a fact, like a viper is a vertebrate, and maybe the language model doesn't know this fact. So if you ask it, is this fact true or false? It says false, but it should be true. Okay, so what are the kinds of cases we're going to be interested in once we edit the model to say this is a true fact? Okay, so previously we had this kind of paraphrase data. So as long as they're like saying the same fact, just in a slightly different way, you want the model to say, okay, yeah, this is the same fact. This is also true. But there's a harder kind of case, which is like entailed data. So statements that are like a consequence of the main input being true. So if you updated a model to know that a viper is a vertebrate, you would also like the model to know or believe that a viper has a brain. This is consequence of something about the way that we use the word, something about the state of the world. If someone believes an animal is a vertebrate, they should believe that the animal has a brain. So these are settings where we're going to want the model to generalize appropriately. Now, in addition to testing for this kind of generalization of the edits, we can also test for overgeneralization. So we want to make sure we're not overgeneralizing to just like totally random other statements, like whether or not Chile is a country, like doesn't really depend on vipers. So like if we change the model's belief in one of the statements, we don't want to change the model's belief in another statement. And then a harder kind of case is actually going to be this kind of like local neutral case is what we call it. These are going to be statements about the same entities, involving the same words, involving the same concepts as the main input, the input that you're updating in the model, but they're at least still logically neutral. So whether or not a viper is a vertebrate doesn't logically entail that it's venomous or that it's not venomous. So if we're teaching the model this one fact, there's other properties that we don't necessarily want to change about this kind of entity. You can make some slightly more fine-grained arguments here, I think, around like, should we adjust the belief at all? Well, don't beliefs seem to come in degrees, or you can make some kind of probabilistic statement about how everything should change. But for now, what we do in this paper is we kind of binarize things and say, okay, these kinds of data should change, the answer should change and be consistent, and the answer should be the same answer. For this other kind of data, the overgeneralization cases, the answers should not change, the answers should remain what they were before. And that's makes it easier for us to test and evaluate. Okay, so I'll describe some basically qualitative conclusions. So the numbers, I think, it's a slightly older class of models, a slightly older class of methods. I think a lot of the qualitative conclusions still hold up, though, when we ask, how well do these model editing methods actually work? And I'm going to tie this into the next research question, which is on continual belief updating. So, it happens that we use this method called hypernetwork weight editing. We're editing this language model called T5 base. What are we really seeing, though? So the main conclusions are that, first of all, fixing one error worked pretty well, but fixing many errors is difficult. And this is important because language models are going to have many errors, and errors are going to compound over time, and the need to edit data changes over time. So yeah, really, there's a lot more work to be done, I think, on making this kind of like lifelong learners, being able to fix an arbitrary number of errors in the models. Number 2, it's harder to fix errors than to create them. This, might seem like kind of a trivial point, like, the important thing is to be fixing errors, right? But it happens that a lot of the evaluation work here and a lot of the benchmarks in model editing often test model editing methods according to their ability to just like arbitrarily change model outputs, not necessarily fixing errors. And so I especially want to emphasize this because like fixing errors is the important thing, and that's the practical use case. So I think this especially deserves extra attention. Number 3, it was harder to generalize to entailed data than paraphrases. This seems to be both a property of model editing methods and also a property of language models themselves. It's a little easier to tell when 2 sentences are like literally saying the same thing versus if one sentence is like a logical consequence of a second sentence. It's generally harder to generalize to those kinds of entailments. Next, it was harder to retain performance on local data than random data. This is an important thing because when we're updating our models, we don't want to be damaging them too much. We don't want to be like messing up a lot of other knowledge in the model. And so it's especially important that if we're updating the model's knowledge about vipers, we want to do, we don't want to do more harm than good. And right now, often like, updating one fact about one entity often there's some incidental damage to the model's beliefs, particularly beliefs that involve the same concepts. Yeah. Lastly, something that you kind of get for free actually is like the fact that updates for improving consistency. Language models have this weird quirk right now that if the model doesn't know the answer to a question, it will often answer you with different wrong answers depending on exactly how you ask the question. So something that's nice about this kind of model editing framework that basically you get for free is like when you're fixing errors, the model can like go from previously inconsistent and wrong to like consistent and correct at the same time. Okay, so these are all qualitative conclusions. I just want to mention too a little bit about what's been going on since this work originally appeared in 2021. Since 2021, I'll highlight this method called minute weight editing from Kevin May and others. They make a lot of progress, I think, on fixing many errors in the model. So, we were saying, okay, fixing one thing is easy, fixing multiple things is hard. They actually could do decently at fixing like 10,000 mistakes or errors in the model. And so, this is major progress for it. Like we were actually struggling with 10 edits. They're doing pretty good at 10,000. No, so okay, so what are the caveats to this? Well, there's still not always entailment evaluation with some of the more recent work, so we still not maybe catching all the hardest cases. And at the same, I'll say entailment evaluation is hard to measure. We adapted some synthetic data from a previous data set, which still isn't perfect. I think I'll highlight there's been some really promising recent work on this, leveraging some specific kinds of relations like very symmetric relations like sibling or like child of or parent of. Um, and and basically the situation right now is that it seems like there is a lot of progress and the methods are getting better. But when people have done some recent and new evaluations focused on these like especially hard cases like entailment, often the model editing methods still totally fail. So you can update a fact in the model like, okay, person A is a sibling to person B, but the model won't even realize that person B is also a sibling to person A as a result. So there's still a lot of important work to do here. Conclusions on this section. Yeah, it does seem like model editing is increasingly useful for fine-grained control. Basically things I've said before, still think we need stronger evals focusing on specifically fixing errors and measuring entailment. Lastly, so talk about kind of an application area of this kind of model editing work, but what I think is, kind of a probably especially important use case going forward. Okay, and it's deleting sensitive info. So we'll refer to ethically sensitive information as sensitive information. We're talking about ethical hazards in the model. In pre-training large language models are known to learn personal information, copyrighted information, knowledge that could be used to harm others. Some of this is kind of trivial, like, okay, how to hijack it, or like how to, hotwire a car. It's like there are already tutorials on that on the internet. There's some speculation right now on like, potentially much more dangerous kind of information in the models, like how to build chemical weapons or biological weapons. Um, I'll leave the speculation kind of aside for now and just say like there's some concern in the community about knowledge that probably chatbots shouldn't be talking about with anyone and everyone. Various toxic beliefs and content. I mean, there's a whole kind of literature on like content moderation and toxicity in language models that I think is pretty well connected to this kind of unlearning area. And lastly, I think this is kind of a cute example, factual information that has simply gone out of date and could become misinfo. The fact that language models are these like static artifacts that like have knowledge cutoffs can become an issue over time when language models don't keep up with what political parties are in power, don't keep up with what figures have been convicted of which crimes or not. Having outdated information can be its own kind of misinfo, and it can be important just for like users to be able to like have an up-to-date system. So I'll make a very generic claim, like we like sometimes would like to remove some of this information from LLMs for ethical reasons. Yeah, a lot of this is going to be super case by case, super sensitive to deployment questions, and deployment use cases and deployment contexts. But this is a very generic motivation for this kind of deletion unlearning area. And then I'll flag that, okay, yes, there are dual use concerns. I've had people ask me, okay, well, what about censorship? What about like people basically misusing these kinds of tools? These are totally legitimate kind of concerns. I mean, the dual use risks are definitely there. Uh, for now, my attitude about a lot of kinds of these like dual use concerns with language models and like techniques for like AI safety kinds of things is that or like responsible AI kinds of tech is that yes, often the dual use concern is there, but like it seems like we just like still need the tooling like to have a chance at like deploying the AI systems responsibly. It's like we at least have to have the tooling. And it might be that other more socio-technical responses are important for making sure that the tooling has not been misused. But that's a generic kind of attitude I have right now. Yeah. Anyway, this is the setup to say that okay, sometimes there are things that we want to remove from image. But what does removing mean? So what does deleting really mean? Okay, deleting information from large language models is totally underdefined. It's not like a database. It's not like a file on your computer that you can just delete it and then it's like no longer there. And in fact, when people have been using current kinds of like safety techniques, RLHF, safety fine-tuning, things that they try to prevent language models from talking about sensitive things with users, these methods are known to basically hide rather than remove the information. So the models will no longer tell you, what the answer to a question is, if it's like a kind of risky or dangerous or hazardous question. But with a little bit of tweaking, this basically various kinds of probes and adversarial attack methods, you can get that information back out of the model. And that's kind of the narrative that we're going to end up following in our paper. And we're ultimately going to cast this as a model editing problem. We want to be able to update individual beliefs in the model. We want to be able to like truly remove the information and not just hide it. Yeah. So this will be research. We're talking about machine unlearning as I think the best kind of um, yeah tie-in and it's like ongoing. It's actually an existing area of research. I'll say more about it in a second. Our paper is on can sensitive information be deleted from LLMs? Yeah, and really the recipe we're going to be following here is something like this kind of adversarial back and forth. So we'll suppose okay, you have a language model. You ask it a question, it gives you an answer. This is answers like somehow classified sensitive info. So what do you do then? You have some deletion defense, like you train the model to say, I don't know. So now you ask the question to the model and the model says, I don't know. Okay, so great. So now we're safe, right? Okay, so really what we're going to be doing in this paper is some kind of adversarial extraction attacks. And we're going to show that often you can still get that answer out of the model even after you thought that it had been deleted. And then, okay, what's the very last thing we do? We say, okay, based on some kinds of these attacks, how can we try to shore up the defense methods and shore up the deletion methods and help them work better? So that's the overall narrative for this paper. So I'll pitch a threat model here, which is basically just how we evaluate things. How are we answering the question, is the info truly deleted? In our threat model, adversary seeks an answer A to question Q. We say, given a model, the adversary obtains some candidate set C of size B, so they have some number of attempts. This is like a budget parameter. And the adversary succeeds if the answer A is in C. So I'll just talk about, kind of some metaphorical arguments here to give this a little more flavor. Why B attempts? Why is it like the adversary gets like a set, like a candidate set, rather than just one attempt? So there's situations that you can imagine are analogous, like password attempt situations. There's an adversary, they get to try some answer like multiple times, like they get multiple attempts to say, can I really like use this information for something nefarious? So it's like a password attempts kind of setting. We have this thing in the paper called like parallel pursuit. Okay, so this is like you can just pursue a bunch of, goals all at once. Like if you're trying to dox someone and you have like their email or phone number or home address, and let me focus on like email or phone number. If their email or phone number is in like a list of like 10 emails or phone numbers, it's still not that hard to dox them. Like you could still do it. It's just you're gonna end up like doxing like 10 people or something, depending on which of the like, identifiers is real or not. So there's this like parallel harm kind of angle. Lastly, something that's like, potentially useful as an intuition for like data owners or auditors in this case. Like it might be like you go and request to Facebook that like your data doesn't get used in their model, or you go request to OpenAI that like your data doesn't get used in their model. And then you go and like ask the model questions about yourself. And like the first time you ask the model a question about yourself, it does not answer the question correctly. But like the 10th time that you ask the model the question about yourself, it does actually still know the answer, or like it does give you the answer at that point. You know, there's some idea of like a tolerance here for like at what level are we tolerant of the model like still being able to repeat this information back to us. No, that's why it's a B attempts kind of thing. Yeah. And I'll say really a lot of this kind of unlearning problem is well established and has been discussed extensively before, but a lot of previous work focuses on formal guarantees of similarity to some kind of retrained model. So it's a lot more formal and focuses on more traditional kind of machine learning systems, and often especially focuses on like simpler forms of data, like tabular data, where you're just deleting like an entry from a table. And it doesn't translate all that well to a setting where like there's a variety of ways you can ask a question to a language model, and the language model's trained on a bunch of data, and there's a variety of ways the answer could be informative or not. So we're not completely trying to reinvent the wheel here. It's just that we do think we basically wanted to pitch our own threat model in our own way to evaluate things here. Okay, so I'll talk a little about the deletion metric, set up the experiments, and then basically the results in this paper are still pretty straightforward. So we'll be able to go through them, I think, in just a few minutes before we hit the top of the hour. So we want to ask, how good is defense? So how good or how well are we able to delete information from models? This is kind of a classic setting where we want to balance two things. We want to make sure that the answer isn't in the candidate set. So that's what we're preventing from the answer from reaching the attacker. And we're not doing too much damage to the model at the same time. So of course, it's kind of like you could delete everything from the model. You could just prevent it from answering any kinds of questions. But that's just going to be like maybe an unacceptable kind of trade-off. The model's no longer useful. So we're going to be trading off between these two things. When we're thinking about actually doing the deletions, this is where the model editing work comes in. We test this, the experiments we run are ultimately tested with some factual model editing data sets like counterfactant CSRE. This is a simplified setting. We filter to questions with single token answers known by GPT-J. So it could be something as simple as like, where is this university located? And the answer is like Madrid, or the answer is Spain. It's like we check that the model knows this answer, and then we try to delete that very simple factual answer from the model. We do this with, so here's some optimizers, AtomW, Rome, and Mimit, different kinds of objectives for like preventing the model from saying something. You could get the model to say something else that's not true. That's like an error injection objective. You could minimize the probability of the answer. We call that factor erasure. Something that is kind of now the canonical response in like an RLHF setting is to say, I don't know, or I can't answer that. We call that the empty response. So we use these kinds of methods for deleting the information from the models. How do we get the information back out from the models? So this is when we're attacking the models. We have two kinds of attacks, basically a white box and a black box attack, although they have some variants beyond that. The general recipe here in the white box attack is that we leverage this insight, this empirical insight that you can delete information from models, and you can do the fine tuning, you can do the model editing to get the model to no longer say the thing that you don't want it to say. And often, often empirically we observe that the information is basically still in the model, inside the model. So when we do a kind of white box attack, or when we do the deletion defense, we often prevent the model from giving the output, like generating when it's generating text. It no longer generates the output. But it turns out that information about the answer is often still contained inside of the model, in the model's hidden states. And so the way our white box attacks work is that there's a really simple kind of probe called the logit lens probe, where you can probe the hidden states of the model at intermediate layers. And when you do this, you can translate those hidden states in the model into vocab terms. And this is how you produce your candidate set then. So you produce like, what are the top translated vocab words for each of the hidden states in the model? And that's your candidate set. And it happens that often that deleted answer is still contained in the intermediate hidden states, even if the model doesn't generate it as like the next token. That's the white box attack. The black box attack is actually, quite simple and basically like a paraphrasing attack. You just ask the question a bunch of different ways. And we suppose that you're at least able to randomly sample from the model. So you randomly sample some different phrasings, and that's how you get a candidate set. Yeah. And you can do this kind of rephrasing automatically. So this attack is still fully automated. There are much more sophisticated black box attacks beyond this. This is like the simplest thing we do, and it'll end up working pretty well still. Okay, so these are the attacks. With the time we have left, I'll say, okay, headline result, you can get the answers back out of the model. So we take this language model, GPT-J, we use the state-of-the-art model editing method with a very standard objective that's like, okay, just say, I don't know, just don't answer the question. And so the model now says, I don't know in response to the question, but using our white box attacks and using our black box attacks, even with a budget of 10, so just trying 10 times to get the answer back out of the model, one of our white box attacks, that's the red line, succeeds almost 40% of the time. So 40% of the time on that list of 10 tokens, you actually have recovered the answer that you thought was supposed to have been deleted. And you can get up to 30% with even the black box method, even with a still reasonably pretty low budget. So still we're able to extract the facts out kind of at a surprisingly high rate of the time. Yeah. Okay, so the last thing we do is improve the defense methods. I think the intuition here is actually pretty simple. I'll focus on the white box setting. The idea here is to delete information wherever it appears in the model. So we notice that information was available in the residual stream, the hidden states. We're going to want to delete that information from the hidden states. The way we do this is that we go into, and so we apply some probes to the hidden states and use an objective term that also minimizes the information content of those hidden states so that the answer token is still not there. Yeah. This pretty simple defense works quite well. So we're able to lower those attack success rates from around 37% to about 2%. This works for basically these kinds of like foreseen white box attacks versus basically kind of slightly unforeseen white box attacks. They like have a slightly different design. So we're still getting seemingly pretty different decent transfer. It happens that when we do these kinds of defense methods, they don't always transfer well between the white box and black box settings. This was a little surprising to us, and I think points the way toward future work. When we think about what would it take to like truly delete some information from a model, we should have one method that like works well against a variety of different extraction attacks. And whether those extraction attacks rely on like probing hidden states versus asking the question slightly different ways. If we think we're robustly deleting the information from the model, I think we should still have, really this strong, clear goal of we should be able to protect against a variety of different extraction attacks. Like that's what it would mean to robustly delete it. And I'll point to the paper for the black box defense. Conclusions here. Yeah, particularly I'll reemphasize the threat model we have. I think we especially want to be focusing on adversarial extraction attacks if we think the information is truly sensitive and truly ethically concerning, if anyone can get it out of the model. Black box defenses were pretty helpful. I mentioned the caveat before about transfer across settings. I'll add that safety standards clearly are going to vary. I also mentioned before, this is very context specific. Ultimately, is a 2% extraction rate safe or not safe? Definitely varies by context. Okay, starting to wrap up a little bit. Here are the goals we talked about: interpretability, fine-grained control, and a bit of an application area, deleting sensitive info. I wanted to situate these things within a broader setting of like, we're thinking about model deployment. We have a language model. We want to be able to ensure that the language model is safe and works as intended. And the research we talked through some human studies on how to properly evaluate explanations for AI systems. Do we really think explanation methods are giving us improved interpretability? And then work on model editing and machine learning, being able to edit individual factual beliefs in the models, individual behaviors of the models, and in a way that seems probably uniquely useful above and beyond these like really large scale pre-training processes. Lastly, just give it a little bit more context with the rest of my PhD work. A lot of this I think is at the intersection of interpretability and fine-grained control, kind of these areas. Especially early on, we did a lot of work focusing a little bit more on this kind of interpretability and explanation faithfulness areas. We're also becoming increasingly interested in these kind of model control things and figuring, okay, like especially like we want to make sure we're doing things that like are actually useful in practice and actually let us like fix errors and make the models more controllable. And then really, I'm particularly excited going forward for just work at the intersection of these things. Being able to leverage improved understanding of how the systems work in order to make them more controllable and make them safer. I'm hopeful that going forward, there will be a lot of synergy between these areas. Okay. With that, I'll end with some acknowledgements. Particularly thankful to my advisor, Mohit Bansal, for all the guidance here and countless little insights about how to make these contributions like substantial and enduring and the field. Many co-authors, too many to name, but wonderful co-authors over the past 5 years here, both internal and external. Wonderful internship supervisors and really fantastic collaborators outside of UNC that have been really helpful for the whole PhD journey. Of course, a number of friends and family members who have provided a lot of support along the way. Also way too many to name, but hopefully many of them listed here. And then, I'm really ultimately quite thankful that I was paid to do any of this. So I'll mention I'm thankful to the funders here, including Google and UNC and grants from the NSF and DARPA. Okay. With that all said, that's the main content, and I'll say thanks, and Mohit, I'll maybe hand it back off to you for the questions or whatever the next various rounds are. But yeah, thank you.